In this video, I want to explore the idea of analogy between different systems a little bit more. And what I want to do is I want to kind of use differential equations to model two different kinds of physical systems. Okay, so the first system that I want to look at is basically a spring mass damper system. Okay, so imagine that you have a wall here and there is a spring hanging from here, and at the end of the spring you have a mass attached, and the mass is m. And as the mass moves, it also is sliding against another wall on one side, or perhaps on both sides. So let me draw a wall on the other side as well. So it's basically sliding here. Okay, now and what is happening is this mass is being pulled by a force F downwards. Okay, now if you draw the free body diagram of this mass, and I'm sure you know how to draw free body diagrams, you have learned it in basic physics. So you have a force F which is being applied. Now this spring, let's assume that it's a ideal spring, and it applies, and it is stretched by, let's say, x. Okay, so it applies a force kx, where k is the spring constant. Also, because the mass is touching the wall on this side and on both sides, there is a frictional force being applied. And let's assume that the frictional force, the constant, is b, and the uh, the frictional friction will be proportional to the velocity. So I'm just writing as bx dot, where x dot denotes the first differential of x. So if we assume that this mass is moving, let's say, with a velocity, with an acceleration a, then we can write the equation for this mass as f minus kx minus bx dot equal to mass into acceleration. Okay, this means that mass into acceleration is the second differential of x, plus bx dot plus kx equal to f. Okay, and I can write this in more standard terminology as b d2x by dt square plus b dx over dt plus kx equal to f. So you can see that this is a differential equation representation of the circuit that we have made here. Sorry, of the spring mass damper system. Okay. Now what we'll do is, let's go into another domain and let's take a look at a RLC circuit. Okay, so let me draw a RLC circuit here. Let's say we have a current source which is connected to a parallel RLC circuit. So you have a resistor, you have a inductor, and you have a capacitor. And let's give some values, C, L, R, and let this current be, let's say, I. Okay, so we know that the current in these three branches, so let me call it IR, IL, and IC. The addition of IR, IL, IC, so IR plus IL plus IC is going to be equal to I, right? So we can write the equation I equal to, what is going to be IR? Let's say the voltage here is V, and let's say this is the ground. So it's going to be V over R. That's the current through the resistor. What's the current through the inductor? It's going to be 1 over L integration of V t dt. And what's the current through the capacitor? It's C dV over dt. Okay, and now you can see that this equation, or probably you cannot see that very clearly, that this equation is very similar to this equation. One way of seeing that would be to actually differentiate this equation. Okay, so if I differentiate it, what do I get? So I get, let's see, so I get a term here. So if you differentiate that with respect to time, you get C d2 v by dt square, plus if you differentiate this one, you get 1 over r dv over dt, plus if you differentiate this, you get v over L, and that's equal to di over dt, which let's say is another function, and let's just call it q for now. Oh, actually q is confusing because q is also used for charge, so let's just use a function called g. And now you can see that this differential equation here is so this differential equation is very similar to the differential equation we have here, right? So this is a second order differential equation with coefficients m, b, and k, and this differential equation is a differential equation with constants c, 1 over r, and 1 over L. So even though we started off with two very separate physical systems, mathematically when we model these equations, they turn out to be very similar. And therefore, if you are able to analyze one of these differential equations and look at the implications of it to, let's say, design a control system, then you can easily transpose that knowledge that you've got into other kind of domains.